we've learned about resistors. We looked at them in the lab this week. Resistors, fundamentally, what does a resistor do? It resists what? It resists charge going through it. So by resisting charge going through, that means that as you force charge through, it's going to take away energy. So we can add resistors the two different ways, and we worked out in lab the equations for how to add resistors in series and how to add them in parallel. So I'm not going to go through and redo those two derivations because we did them in lab, and instead go forward to what do we do if we have a complicated arrangement. If we look at the circuit on the left, you see that we have resistors in all kinds of arrangements. And as is indicated by the circles, you can simplify your circuit by saying, well, it's going to work exactly the same as if I replace those three parallel resistors with one resistance. So this resistance here is going to be 1 over Rp is equal to 1 over R2 plus 1 over R3 plus 1 over R4. And this one here is going to be 1 over Rp prime is equal to 1 over R5 plus 1 over R6. And then when you replace those parallel combinations with an equivalent resistance, now we see that those two parallel resistors are in series with each other. How do we identify? Remind me, like I'm, say I have amnesia, or that I'm old. What does it mean for two resistors? I'm not. Okay, not. When you always define old as like 20 years older than you are presently. And so by your definition, I know I'm old. Jerry laughs. But my definition says, yeah, I'm young. It's my folks that are old. Okay, so what does it mean for them to be series? What does that mean?
They come one after another on the circuit.
They come one after another. A very important key is there's no other option for where charge can go. If charge goes through one, it has to go through the next one if they're in series. You can't have an alternate route. If they're in parallel, what does that mean? Go, John, this time.
It could go through either one.
It means that you can have charge go through either one, but the starting point and ending point is the same. So the top and bottom are connected together. Now, if I look at my original picture, how is this resistor compared to this resistor? Series or parallel? Okay, it was a trick question. It's neither. It's neither series nor parallel, because to be parallel, you have to have the tops connected together. But those tops are not connected together. To be series, there has to be no option, but for the current that goes through one to go through the other, it's not in either of those situations. So we're going through to simplify, taking the things that we can identify as series or parallel and combining them. So in this picture here, we have these two resistors in series, so those are combined. So this Rs is equal to Rp plus Rp prime. And then we see now we have this resistor is in parallel, with that combination that's made up of actually combining 5 resistors. And so then we take those that are in parallel, we add them up to get, what do you call it here? Rp double prime. And I'm not going to write the equations anymore because we've done that enough. And then you have these two in series and you get Rs prime. A lot of work to find the equivalent resistance. Why would we ever do a problem like this? There's only one reason. It's not a good one. Yeah, to drill stuff into students. In real life, you don't make a circuit that looks all that much like this. How is this useful? If you had a real life circuit like this, why would you ever want to find what the equivalent resistance is for all of those resistors? Not seeing it, are you? The reason would be because you want to find out what load the power supply sees, so you can determine how much current it needs to produce, and thus how much power it will be. Remember, power is voltage times current. I went through that once before. And so if I calculate what that equivalent resistance is, then I can use Ohm's law and say, well, the current is equal to the voltage over the resistance. And so that means the power is equal to the voltage squared over resistance. And I can calculate how much power I need for my power supply. So that's why you would actually want to do that if you, for some reason, have this crazy circuit. Reality, it's to drill it into you, right? So here's a circuit, and the problem says how much current has to be provided by this 12-volt battery. So let's go through and do the work. So what should I do first? Combine R2 and R3. Why did you choose to combine R2 and R3?
Because they're the only two that are actually either in series or parallel.
Right. They're the only two that are actually either in series or parallel. Some people, before they really understand series, might say, well, R1 is totally in series with R2 because current can go like that. They're connected together. But the key is to be in series, there has to be no other option, and there's another option. So Jonathan was right. Just R2 and R3 are in parallel. So I will have remember, I kind of disdained this equation and now I use it. I disdain it because it gives people the wrong idea of how to add resistors in parallel. But it works perfectly if you only have two in parallel. And so since it's only two, I went ahead and used it. So that's my R parallel. So putting in numbers, that's going to be 6.00 ohms times 13.00 ohms divided by 6.00 ohms plus 13.00 ohms, which is 78 divided by 19. 0?
Or 1, 1.
Okay, so we have 3 sig figs, so we got to keep at least 3. So 4.11 ohms. Now that I've done that, my circuit becomes the much cleaner looking. So what's the total resistance now? Yeah, you just add them together. Everybody can do that in their heads. So what's the current? Tell me the equation first. V over R. And the units are amperes because we had volts and ohms. So we have 2.35 amps. What's the voltage drop across resistor 1? Good. You say it out loud, Aaron.
Is it just 12 volts over the first resistor?
Not 12 volts. Remember, Ohm's law, V is equal to IR. So what's the current going through that resistor? 2.35 amps. So what's the voltage then?
Yeah.
2.35 volts. I thought I'd heard you say that, so that's why I called on you. So what's the voltage across R2? There is a quick way to calculate it. You can do it in your head. I'll write down the answer. Anybody see how I got that? Gabriel?
When you say R2, are you referring to R2 combined with R3?
Well, R2 is an individual element, so I can just say R2. R3 has to have the same voltage drop because when things are in parallel, they always have the same drop because the top is together, the bottom's together.
So you take the initial voltage,
12 volts.
12 volts, and then subtract the voltage across R1.
That's right. I just took the 12 volts. I start with 12 volts of electrical potential. I go down by 2.35 on the first one. How much am I left with? I'm left with 9.65 because 12 minus 2.35 is 9.65. So that's how much remained. Now that I know how much the voltage is across those two, I can find what I2 is and what I3 is. So let's do that real quick. I2 is equal to V2 over R2 is equal to 9.65 volts divided by 6.00 ohms, 1.61 amps. And what about I3? Same 9.65 volts because when they're in parallel, they have to have the same voltage.
0.742.
And now the last thing, if I had 2.35 amps coming out of resistor 1, how much current do I have to have when it splits between resistors 2 and 3? The total has to be 2.35. Because if I have 2.35 coulombs coming into there each second, I have to have 2.35 coulombs leaving each second. And so the two numbers had better add up to 2.35. So you add them together, 6 and 7 is 13. 1 and 4 is 5. Comes out to 2.35. So was that hard or easy? Okay, generally speaking, that's easy. This is a simple circuit. We're going to learn in one day to do complicated circuits. How many people took circuit theory already, or electric circuits? Only 2? Oh, 3. Okay, 3. You didn't take it, Gabriel or James?
I think
No. Okay. Well, we'll learn what they learned in, half a semester in one day. Obviously, they learn it better. First, a little talk about batteries. A battery, and of course, I didn't put back in the pictures of how a cell works. But a battery is a combination of cells, and each cell is an electric or a chemical reaction. And the chemical reaction is between, like in a lead acid battery, the chemical reaction is between a piece of metal and a liquid. And when you have a chemical reaction between that metal and the liquid, you start building up residues. And so over time, you start having other materials that have formed start to interfere with how well the reaction can occur. And so the reaction rate slows down. If the reaction rate slows down, that means it takes you more time to give energy to the charge. So a brand new battery will have generally a fairly quick reaction rate, which means it can supply a fair amount of current. A bigger battery just has more space for the chemical reactions, and so it can provide more current because it can do more reactions per second. But when they get old, the reaction rate slows down because you built up crud. And so old batteries start to fail. If you measure the voltage when you're not using it, it'll still show a full voltage until it's really on its deathbed. But as soon as you start to use charge, to use the battery, then the voltage drops because the reaction rate can't keep up. So the best way to check a battery to see if it's done is to put it under a little load and see if the voltage drops. And because the chemical reaction is not an infinite rate, anytime you put a load on, it's going to drop a little bit. And so for physics, we approximate a real battery as being an ideal battery, so this here is the ideal battery, in series with what we call the internal resistance. So that internal resistance is a resistance value to account for the fact that the reaction does not occur instantly, that it takes some time for the reaction to occur. And so the more current you use, the more the voltage is going to drop because the reaction can't keep up. And so we have now a terminal velocity. So I put this dashed box around here, and that's my real battery. And the real battery is going to have a terminal voltage equal to, and that's supposed to be a script E to represent the electromotive force, the EMF, minus the current going through the battery times the internal resistance. So that's the terminal voltage. The more current you're drawing from the battery, the lower the voltage goes. For a good battery, what kind of value do you expect you should have for the lowercase r, the internal resistance? It should be small. For a good battery, that internal resistance is a very small number, like half an ohm or so. But as a battery gets old, that internal resistance goes up, which means that as soon as you start using it, the terminal velocity gets lower and lower. And so that's, once again, why you test it under load. And so for this simple circuit, if I use Ohm's law now, I have two resistors in series, the load resistor and the internal resistor. So the total resistance is the sum of those two, and I can find the current is the EMF over that total resistance. Complicated circuits. Find me a series, two resistors that are in series in this circuit. Okay.
Little r sub 2 and big R sub 3.
Okay, little r sub 2 and big R sub 3. These two here are in series. So I can combine them. Now, a little more tricky, but big R sub 1, or big R sub 2, excuse me, and lowercase r sub 1 are in series with power supply E1. And so those, because all three of these are in series, I can actually combine those resistances as one in series as well. But then how do those relate to R1? They're neither series nor parallel because the tops and bottoms aren't connected together. And current that goes through R1 doesn't have to go through capital R1. It can go through R3. So here we have R1 is not in series or parallel with anything. So I can't simplify this circuit the way we did before. So solving this circuit is going to take a little more complicated, a little more complex method. And to do that method, we have to introduce Kirchhoff's two laws. I've actually used both of them, but we haven't specified them. Note how Kirchhoff is spelled because some people pronounce it Kirchhoff. I learned it as Kirchhoff. Double H and double F. It's a really unique spelling. To me, at least. Double H's aren't common. Kirchhoff's current law is a statement that charge is conserved. What does it mean to say charge is conserved? I'm pretty sure somebody answered correctly, but I did not understand all the words. Okay. Gabriel had his hand up.
It doesn't disappear somewhere in the circuit, so the amount of charge to start with is the amount you have to end.
Okay. You can't create or destroy charge. Now, that is not to say you can't create or destroy charge carriers. You can have particle physics interactions where you started with two photons and you produce an electron and a positron. But the net charge you started with was 0, and the net charge you ended with was 0. Charge wasn't created, but individual charge carriers were. So charge is conserved. You can't create or destroy total charge. There's another caveat that goes for everything we do in electric circuits, and that is nothing in the circuit stores or delivers charge. And a lot of people, if they haven't thought about it carefully, take offense to that statement. Because what does a capacitor do? I say a lot of people, I did. Okay. What does a capacitor do? Stores. You have to have another word. Doesn't store charge. Stores charge separation. The capacitor doesn't store charge. It stores a separation of charge. And so the net charge on a capacitor in an electric circuit isn't going to change. You're just going to move charge from one side to the other. So it's not storing charge or delivering charge. What is a battery doing? It's giving energy to charge. Technically, a current supply is moving charge, and a battery is giving energy to charge. The outcome, of course, is you give energy to charge, and it's going to move if you provide a pathway. So we have those two caveats in blue and red. Charge is conserved, and nothing stores or delivers charge. So that means if I have a place where two or more wires meet, and here's a new word for us, node. So a node where two or more wires meet. So if we look at this picture here, there's a little dot and A to indicate a node. How many wires meet at node A? 3. If we have 3 or more, we call it an essential node. What's essential about an essential node? You don't really need to think about nodes where only 2 wires meet because any charge going through there just has to keep going, right? And so we don't worry about the nodes that's just, well, this wire meets this wire and the charge goes through. But when we have 3 wires, then we have to start thinking about, so how's the charge going to move? Is it going to go down path 1 or down path 2? And so essential nodes are where we have to start thinking about it. And Kirchhoff's current law says at any node, the sum of the currents equals 0. Now it says sum of the currents. Is that currents in or is that currents out? No one cares. You could say the sum of the currents in equals 0 or the sum of the currents out equals 0. If you say the sum of the currents in equals 0, then out is negative. And so it'd be in minus out. If you say the sum of the currents out is 0, then in would be negative. And you would have out minus in. Well, it's still going to be 0. Another way of saying it is the sum of the currents in equals the sum of the currents out, where you're saying the positive both ways, but you have to put on the right side equal sign. The whole point is whatever comes into a node has to leave the node. And so that gives us a mathematical equation there. I've written it 2 different ways. So we utilized that in the problem we did earlier. We just didn't have a name for it. I think Kirchhoff had to have been a just blazing genius because he takes 2 really obvious things and everybody knows him because of those obvious things that he gave them names. So in this example, coming into the node is I1, leaving the node are I2 and I3. So if I say coming in is positive, sum of the currents is 0 means 11 minus 4 minus 7 equals 0. That's Kirchhoff's current law. Gives us equations in a circuit. Clicker question numero uno. What law is Kirchhoff's current law a restatement of? Okay. It's all on you, Sandy. You have to answer because there's only 2 clicker questions. Okay, we had a dichotomy here. Talk to the people around you to understand better. It was in the concept coach. It was in the concept coach. It's just a split. Well, not everybody gets the same question.
Really, they don't have to switch every time.
Okay. Before Jonathan explains this to you, let's go ahead and answer again to see if after talking to your neighbor you were able to come to a better James and Nate. Okay, James? Okay, you are going to laugh. We didn't really clarify anything in our discussion. So, Jonathan, it's up to you.
I guess part of the most of the reason I chose B. Most of the reason I chose B was because it was in the concept coach. But the other reason, I suppose this could go either way. But I was just thinking, like, since all of the energy that comes into it has to be negated, so there's a conservation of energy. I don't know if that's what you're looking for.
Okay. Now, unfortunately, you chose the wrong one. The equation is sum of the currents at a node equals 0. Current doesn't have to do with energy explicitly, right? You have to have a resistance involved for it to give us something about energy. And when we're at a node, we're not dealing with a resistor. So it's not dealing with energy explicitly. What it is dealing with is the motion of charge. And so the correct answer was D here. Conservation of charge is what Kirchhoff's current law is dealing with. Now fret not, because there's another question coming up. Kirchhoff's voltage law. Kirchhoff's voltage law is the law that says energy is conserved. It's the voltage law, not the current law, that has conservation of energy. So remember, voltage is the potential energy per charge. And what this says is if I start somewhere and I go through the circuit, so go through the power supply and your energy per charge goes up. And then you go through a resistor and it goes down. That's a downward slope. The wires ideally have 0 resistor, so this is staying a constant height. Then we go through another resistor, lose energy, constant here. Go through the final resistor and lose energy. And we'd better be back to where we started. If you weren't back to where you started, as an electron went around the circuit, let's say that you ended up 1 volt higher every time you go through the circuit. You would eventually have an infinite voltage, right? Well, that doesn't make sense. We can't have a circuit that keeps running for any period of time if you're going to gain energy each time. Likewise, if you lost energy each time, you would end up with negative infinite energy, whatever that might be, after a while. So just like with a heat engine, you have to have the energy difference for one complete cycle is 0. And so that's what Kirchhoff's voltage law is. It says energy is conserved. We're not creating or destroying energy We're just moving it around. And so mathematically, that's written as on a loop, not at a node anymore, but on a loop, a closed loop, so you come back to where you start. The sum of the voltages is 0. And many times we'll write that as the sum of the voltage rises equals the sum of the voltage drops. And so you'll see different people rearrange the equation multiple ways for what fits their fancy. But the key is energy is not created or destroyed. So what was Kirchhoff's current law a statement of? Conservation of charge. And what's Kirchhoff's voltage law a statement of? Conservation of energy. So both of these are fundamental physics ideas. And I've got a good sense that people are going to get this right. So Kirchhoff's voltage law is a restatement of which principle? Thank you. You were trying to raise my blood pressure, and it was working. I was really concerned. We still have one person who refuses to play along. I'm not going to ask anybody to explain this. I think we should all understand now. Conservation of energy is what Kirchhoff's voltage law is. How are these useful to us? I've just given you 2 laws. A law isn't any use. Okay, that's dumb. That's what we call, was it a tautology? A law is not useful unless there's a way to use it. So we're going to learn how to use it in exactly one slide. Before we get there, the relationship between voltage drop and current is important. When current goes through a resistor, it loses energy. So we always need to have a direction for the current to associate with the voltage drop. So on the left there, I have a resistor with current going from the left to the right. Where did the charge have more energy, before it entered or after it left the resistor? It had more energy before it entered. So if the current is going to the right, that means this side here, the tail of the arrow, because the arrow is shown going over the resistor, is where the positive is. And the head of the arrow is where the negative is. So in the picture on the right, which side is positive? Okay. And I know it seems really silly to have you do it a second time, right after we did it the first time. But it's important to make sure people understand, okay, I have current going this direction. I can tell you which side's positive and which side's negative for the voltage drop across that resistor. Now for the power supply, so I have a single cell shown at the bottom. What direction should current flow naturally? Out of which side? Out of the positive. So in this case, I'm going to draw a current arrow. And notice now I have positive on the side of the tip of the arrow. Not meant to confuse, but meant to make you remember, what is the power supply doing? It's adding energy. Yeah, it's adding energy. And so that's why the voltage went up when the current went through, because it added energy. The resistor, it's taking away energy. That's why it dropped as it went through the resistor. So you have to remember those directions. And when we talk about power, for a resistor, well, always power is equal to VI. For a resistor, the power is always going to be power dissipated. It's taking energy out of the electricity. For the power supply, it's the same equation, but it's power supplied. And how can we determine this one here is positive and this one here is negative? Because the current and the voltage directions are opposite for the two. If you go up in voltages, you follow the current, then it's adding energy. If you go down in voltages, as you follow the current, you're losing energy. So, and once again, I was in circuits class, and I just really wasn't clear on how can I tell if it's dissipating or, or adding energy. Resistors always dissipate. They always absorb energy. A power supply can add or remove energy. If you put it in the circuit backward, it'll remove energy. So you have to pay attention to which direction the current arrow goes compared to the voltage to determine if it's going to absorb energy or supply energy. And of course, in reality, you don't want your power supply to be absorbing energy. Right? Seems like a waste of energy to use energy to absorb energy. Agree? So ideally, you don't do it that way. All right, so here's the circuit. How do I find the currents and voltages in this circuit? Like you're going to do in the next lab activity. You're going to do exactly like what we're going to do here for the rest of the class period. What to do?
We'll find the ones that are in series and parallel.
Okay, find the ones that are in series and parallel. But we already talked about that. Like R1, it's not in series or parallel with anything. Now, we have some students, the back row students, who've already learned this. But here is your process. Step number 1. Step 1. Identify your currents. Now, in this figure, the currents are already identified. Actually, I think I had this circuit before without them identified. Nope, not that circuit. Yeah, here is the circuit without it identified. And so let's look at this one to start identifying the currents. So when we identify currents, oftentimes we get on the small scale and we say, well, there's a current through capital R1, there's a current through capital R2, and there's a current through capital R3, and there's a current through E1, there's a current through E2, and there's a current through lowercase r1 and a current through lowercase r2. But that's, as like we'd say, micromanaging, because when we have things in series, such as capital R2, E1, and R1, what did I say about the current? It has to be exactly the same, because any current that goes through R2 is also going to have to go through E1 and also have to go through lowercase r1. So I define a single current for what we call a branch. Goes from essential node to essential node. How many essential nodes do I have in this circuit? 2. So this is going to be another step. I'm going to label my essential nodes A and B. So it's going to be another step, but I did it right now. And so I'm going to have currents, and I'll call these branch currents that go through each branch. And so I'm just going to call this one here current 2. Why do you suppose I drew it in a clockwise fashion? It is the way it's going. I was smart. How did I know it was going that direction? Because be specific. Talk about the power supply. Yeah, it should come out of the positive end of the power supply. Now, sometimes you'll have a circuit where you can't tell. But here, I can tell. Okay, so there's current I2, current I1. I'll do I3 next. I3 I'll make like this. Once again, coming out of the positive side of voltage supply 2. And then I1 I'll go like this. So I identified my currents. Did all on my own. Which is why I was on that slide, not this one where they're already labeled. Now notice here it's separated I2, I2, and I2 just to illustrate things. So step 1 was identify currents. Step 2, identify which side's positive and negative for each element. So let's start with the very easiest. It's actually already marked, branding. what is the positive side for the voltage supply E1? E1 is the one on the top.
Oh, 18 volt.
Which side is positive?
Right.
Use A, B, C, D.
Oh, C.
C. Okay. And it's marked there already because that was the positive side of the power supply, right? So I go through and I mark this. I go ahead and put minus on one side and positive on the other. I'm not going to rewrite the positive. Now going a step more difficult, Isaac, when we get to R1, what direction is the current going through I1?
Towards A node.
Oh, okay. I forgot. There's two R1s. Lowercase R1 is the one I was looking at. I was looking, what are you talking about? Through lowercase R1. It doesn't have an arrow mark there, so that's why I was asking.
It's still going clockwise, isn't it? It's going
So is it going toward C or toward D?
toward D.
Okay. So I always write my current right there so it's very clear to me. So there's I2. And then once he's done that, Katie, which side is the positive side for the resistor R, lowercase R1?
What side is the resistor?
Which side is the positive side of the resistor? Which side has higher voltage? It's the other one. You have the positive is on the side of the tail because the current is going into C and out of D, right? In terms of that resistor. It came in on the C side and went out on the D side, according to the way the arrow is drawn. And since the resistor took away energy, it had to be higher on the side that the current went into it than on the side it came out of. Uh-oh. And it's very important to be able to identify these. If you can't identify those correctly, you can't solve your circuit problem. Okay, so now we go through the rest of them. Capital R2, Hannah. Which side would be positive there?
Can you point out where R2 is? Okay. Well,
It's somewhere on the screen.
okay. What was the question?
Which side would be the positive side for resistor R2?
The bottom side?
The bottom side is correct. And why was that?
Because the charge is going away from it.
Okay, that's the side it enters. And so it's positive on the side it enters, negative on the side it exits.
Okay.
Yeah. I think that's what you were saying, right?
Yeah.
Kind of.
Yeah.
Okay. This version of R1. Larissa, which side is positive for this one? The right side. Right. Because the current is going like this, so the tail, positive, the head, negative. R3, Mahala. Which side is positive, top or bottom? Correct again. This doesn't have an arrow, so I'm going to draw the current arrow so we don't forget. Going next, Megan. Which side's positive here? Right. I think this one here, since it already has positive, I'm not going to ask anyone. I'm also not going to put positive on both sides. Okay, so we've gone through and we've marked positive and negative on every single element. So that was step 2. Now step 3 is where it gets fun. Identify number of loops equal to number of meshes. Okay, what the heck am I talking about now? For Kirchhoffs voltage law applies to a loop. And so we're identifying loops to use with Kirchhoffs voltage law. But you can't use every possible loop. How many loops can I make in this circuit?
3.
I can make a total of 3 unique loops. But I can only use the number of, quote, meshes. and a mesh is a smallest loop possible. So if we look at this, the meshes would be the top loop and the bottom loop. The outer loop is not the smallest possible. So there are two meshes. So I'm going to identify two loops because there are two meshes. If I identify a third loop, it turns out that it's just a linear combination of the first two. So that's why I can only do as number as I have meshes. I also need to make sure I cover the whole circuit with my meshes. So I look here and I say, well, I am going to use this here as mesh 1, or loop 1, and this here as loop 2. Notice I showed a direction, because I'm going to go around these in a specific direction. Step 4, apply Kirchhoffs voltage law to each loop identified. So I will do the first one, and then I will call on the next person would be Caitlin. Actually, you know what? I'm going to make it easy for you. I'm going to call on Carrie because Carrie's already been through circuits class, and it'll be easier for her. I'm going to do the first. Oh, heck. Carrie, no. I'll do the first one so you see. When you do your Kirchhoffs voltage law, you can start and stop anywhere you want. I always start at the bottom left-hand corner simply because, actually, you know what? I'm going to change the direction of, I always also make my loops go like this. I always make my loops go clockwise and I always start at the bottom left-hand corner. I do that so I never get lost. Go ahead.
Can your loop go in the opposite direction of the current?
Yes, it can. That's why we went through and put the plus and minus signs everywhere so we can keep track of these. So I am going to do loop 1. Sum of the voltages on loop 1 equals 0. So I look here and I'm going to start at A, and if I go from A to B, did my voltage go up or down? Down. Minus. I have the current I2 and the resistance R2. How do I find voltage from current and resistance? Ohm's law. And so that's just going to be minus I2 R2. Okay, so now I'm up to B. Going from B to C, did the voltage go up or down? Up. So I'm going to have a plus sign, E1. Going from C to D, did the voltage go up or down? Down. So minus I2 lowercase r1. Going from D around to E, what do I have? Nothing, right? And then going from E back to A, down, minus I1 R1 equals 0. So there's my equation. Now, Carrie, following the way I did it, starting down here at this point and going in a clockwise fashion, what's the first element I get in loop 2? Okay, plus I1 R1. Why did she use plus there? Because I was going against the current. It was going from the minus to the plus that we wrote. Okay, then going from E down, what do I get? And then going through lowercase r2. And then going through this power supply. So there's two equations. How many unknowns? My unknowns are the current. How many unknowns do I have here? 3. Linear equations, I have to have the same number of linear equations as I have variables. So I need one more equation. So there, that brings us to step 4 or 5. Identify the essential nodes. Which ones are my essential nodes here? E and A. Step 6. Apply Kirchhoff's current law to one less than all essential nodes. So since I had 2, I only do it on 1. Which node should I do it on? E or A? Name it. A, okay? So sum of the currents on node A equals 0 equals, looking at node A, I1 comes in, I2 and I3 leave. So now I have 3 equations, 3 linear independent equations. We're out of time. If you don't know how to solve these using linear algebra, I strongly recommend that you look at, I'll save it right now. Okay, it's saved. That you go and look at the rest of the lecture where I go through how to use your calculator to solve these really, really easily. Because if you don't know how to use it on your calculator, it can take you a long time to solve it once you have these equations. But if you know how to do it on your calculator,